So today's lesson is on derivatives of inverses. Do you remember what an inverse function is?
Yeah.
Are you lying to me? It means if you have a function and you take the domain and range and you flip it, that now becomes the inverse. And to find the inverse, if that's what you ask, you take x and y, right? Substitute for each other and then solve for y, do inverse operations. So it says at the right are graphs of f at x, and the symbol for inverse is that little -1. And so one of the properties of inverses and their functions that they always reflect over the line y equals x. So if there's a point on f at x that's AB, then the point BA has to be on the inverse by definition, that x and y are flipped. So from the graphs above, do you see a relationship between the slope of the graph of f at AB and the slope of the graph of f at -1, or the inverse, at BA? So can you see at BA, if I drew like a little cute little line, right? And if I see a cute little line here, what do you notice? So do that, and then look. And what do you notice about the two slopes that you have? Opposite. Is it the word opposite that we want?
Inverse.
Is it the word inverse that we want? So what do you notice about one slope compared to the other slope? So I heard the word opposite, right? If it's the word opposite, that would mean that one would be positive and one would be negative. Is that true? When looking at that, is one positive and one negative, the slope? Or are they both positive? So it's definitely not the word opposite. What's the other word you want to use? Inverse refers to operations. Like the inverse of adding is subtracting. What's another word? Close. I like the re part.
Reciprocal.
Reciprocal of one compared to the other. So reciprocal, because what's going to happen here is you're going to be confused when two slopes are perpendicular. Do you know what you do? It's the opposite reciprocal, correct? But for derivatives here, it's not the opposite sign, it's just the reciprocal. So you keep the sign the same. All right, let's look at example number 1. If I asked you to sketch root x, could you? Say yes confidently. What point should I put on my graph? I like that. I like that. 4, 2. I like that. Does it go forever? To the right, but not to the left? How about the inverse? How would I find it? So if x equaled root y, what would y equal? We need a domain restriction. Do you know why? Because the range of the function has to be equal to the domain of the inverse. So we just said that the domain is x squared, but that's not the full parabola. What's the range of the square root of x? It's 0 and above, right? That means my domain has to be 0 and above or to the right. That means there's no negative numbers in the domain. So what would this parabola look like if it's only the positive x values? What points do we have? X squared, only positive, and 0. So 0, 1, 1, and let's do that. If I did draw the line y equals x, they would reflect over that line y equals x. So that's A, B, and C. What's the derivative of both of them? So let's first look at f at x. How do I take the derivative of root x? Remember, whenever we have a radical sign, or whenever we have a fraction, we always change it to an exponent first. What exponent should I change it to? And now what's the derivative? 1/2 x to the negative 1/2. How about the second one? The inverse of f at x was x squared, and we had a domain restriction. What's the derivative of the inverse? So if I took the derivative of this, it would just be what? 2x. And we know that all x values have to be 0 or greater. Perfect. E, what's the slope at 4, 2? Do you see this point 4, 2? What's the slope? How do I find the exact slope? Plug in. What x value will I plug in? So can you plug it in? So if you plugged in 4, remember the derivative's right above it. We're going to clean this up a little, okay? So where there's an x, I plugged in 4. Do you have the number sense to clean that number up? What does the exponent 1/2 mean? What is the square root of 4? And then, do you know what the negative does? It's the reciprocal of the base. So if the square root of 4 is 2, what's the reciprocal of 2? And there you go. And then you multiply across the tops and bottoms. What's the slope there? Does that make sense? Like, look at it. Does it look like up 1 over 4? Reasonably? All right. How about we take the point on the inverse, which is at 2 and 4 up here. What would that slope look like? Is it also positive? Is it steeper or not as steep? So you'd expect the answer, right, to be larger than 1/4, correct? Because it's steeper. So what number do I then plug into the inverse? Is what number for x? 2. And what's the derivative at 2? Well, 2 times 2 is 4. What do you notice about the... What conclusion can you make? So, if you take the derivative of a function, right, and its inverse, the slopes are reciprocals. Yeah, it's 4. Sure. So what relationship does a function and its inverse have for derivatives? The derivatives are, if there's like the point of the lesson today, there it is. So when you have a function, it's inverse, right? The relationship of their derivatives is what? They are reciprocals of each other. Okay. So look down here at the box. It says if AB is a point on a function, that would mean that BA then would be a point on the inverse. And that means if you take the derivative at that point of the inverse, it is that's a fancy way of saying reciprocal. Notice one takes the x coordinate and the other takes the y, because you are flipping it, right? The y becomes the x. That might be a little, take practice so it doesn't flip you out in your brain a little bit. But the concept of the reciprocal isn't that great. Just reciprocal, the derivative and so on. So, or if f and g are inverse functions, then again the derivative, and here, if you know their inverses, then you know the relationship is reciprocal. So derivatives of inverses have reciprocal slopes at image points, points reflected across y equals x. So A, B, and BA are what are called image points. Let's turn the page. This is the point I was trying to make. When finding derivatives of inverse functions, do not use the same x value for both. Why? Because for your inverse, your y value becomes your x. You can't use the same x value twice unless, it's the same number for x and y. So, let f and g be inverse functions. So we are told that f and g are inverse functions. Notice that f at -1 equals 1. That's not a derivative. What's it telling you? That a point, right, which is at -1 and +1. What's this point? What's this point? That means I also know the inverse, right? So if I flip these, I'd find points on the inverse. Good. And then it tells me the derivative at what number? -1, the derivative at 0, and the derivative at +1. Notice using the x values of the function, not of the inverse yet. It says, what's f and g are inverses, so what's the derivative of g at 1? Well, for the function, if they're inverses, the y-coordinate becomes the x-coordinate, and what's the relationship? So the answer there is 2/3. How about for b? Remember, the y-coordinate becomes the x-coordinate, and what relationship is it? It's the reciprocal. So what's the reciprocal? 1/2. Don't change the sign. How about the derivative at 3? What I'm looking for is, do I know the y-coordinate 3 on any of these? So guess what? This can't be determined, because you don't have the point you need. You need a point where the y-coordinate is 3. How about the derivative at 0? Do any of them have a y-coordinate at 0? Again, it can't be determined with the information given. How about the last one? The derivative of 5. Any y-coordinates 5?
Yeah.
Good. So what's the derivative there? The reciprocal of 1/2 is 2. If a function f has an inverse, f at -1, or f to the -1, then f is 1-to-1 and must either be strictly increasing or strictly decreasing on its entire domain. We can use the derivative to find out where f is increasing or where f is decreasing. So, 100 years ago, I talked about the horizontal line test, about 1-to-1. What happens if you have a local min or max and a local min? What's going to happen? So if I draw something with a local max or min, it's going to fail the horizontal line test. That means if it's a 1-to-1 function where you can find its inverse, when you do the first derivative test, it all has to be positive or it all has to be negative. It can't switch, because as soon as it switches, you can't take the inverse of it unless you do a domain restriction. Say, okay, you're only going to do the inverse from here to here, only. But you can't have sign changes for 1-to-1. All right, so it says show that that is not 1-to-1 on its entire domain. So to do that, first thing I'm going to do is find the derivative of f of x. What's the derivative? 6x is just 6, and negative x cubed would be negative 3x squared. Make it equal to 0. What we're testing to see is if there's any local max or mins, to see if it actually changes from increasing to decreasing anywhere. So how would you solve for x? Subtract 6? That's what I would do. What would you do next? Divide, and negative 6 divided by negative 3 is, and then how do you undo that? And make sure it's positive and negative. Check the domain restriction. It says the entire domain, so both positive and negative root 2 we're going to look at. Draw first derivative number line. What numbers am I going to put on there? Negative root 2 and positive root 2. What am I testing for again to see where it's increasing and? So use the derivative. What's a nice number that's smaller than negative root 2? 0 is not smaller than negative root 2. What's a nice number smaller than negative root 2? Negative 2. Yes, negative 1 is actually bigger than negative root 2. So negative 2. If you plugged in negative 2, what would you get? 6 take away 12, which is negative. You get what I'm saying? Now we can do, what's a nice number between negative root 2 and positive root 2? 0. If I plug in 0, what do you get? 6, right? Good. And plug in whatever, a huge number, and the answer is going to be negative. What do you notice?
It's not monotonic.
Why?
Because it switches.
And you're right, monotonic means mono, right? One. So you'd have only one sign. All right, B, find the largest interval containing x equals 0 for which f is 1 to 1. So now we're going to do a domain restriction. So what's the biggest interval where we have one sign? And it has to include what number? 0. So from negative root 2 to positive root 2 is the biggest interval that is monotonic, right? And you could do a domain restriction there, and it's 1 to 1, because it's only one sign from negative root 2 to positive root 2. Find the largest interval containing x equals negative 2. Do you remember where that is? X equals negative 2? So negative infinity to... So all the way to negative root 2, the sign doesn't change. Know that at negative root 2, the sign's actually 0, right? It's neither positive or negative. That's it. So what was the big part of the lesson? A function and its inverse, right? What's the relationship of the derivatives? They are reciprocal. Beautiful.